Hello, welcome to a new video on sagemath. In this video we are going to discuss various ways of finding derivatives of functions which contains one variable or two variable or more than two variables. Mainly our attention we will focus on the derivatives of functions containing one variable and two variables. See, the syntax of the of sagemath command that can be used to find the derivative is given here. You can see that to calculate the derivative of a function we use diff command. Diff in bracket you can put the function, you can use the function whose derivative we want actually, or another way you can find the derivative using by using dot derivative command. Dot derivative. So we have two commands, diff bracket and then and dot derivative command. See, this is the way we can write an expression for finding the derivative using diff in bracket fx. You can use fx or fx dot derivative. Fx dot derivative, by using derivative you can write it first typing first giving the function fx. The function should be written first and then dot can be used to connect it with the derivative command. Now to differentiate the function f of x, y, f of x comma y with respect to x, see, using diff command, it can be written diff back and then bracket inside the bracket f of the given function f of x y and comma you have to give x to specify that the differentiation must be done with respect to x. On the other hand, if you want to obtain the derivative with respect to y, you must replace x by y. In this expression you can replace x by y to obtain the derivative with respect to y. So this kind of differentiation is partial differentiation. So this way you are going to get partial derivatives. See, partial derivatives are the derivatives when the expression contains two or more variables, independent variables. To compute the nth derivative with respect to x, see, suppose you want the nth derivative with respect to x of a given function, you can then write the command as diff then bracket, you can start the bracket and inside the bracket you can write fx and then comma with respect to which variable you want to differentiate, that can be given next. That's the variable x and then comma. After that you can give the number of or the degree of the derivative, the level of the derivative that you can give, that is the nth. You can give there the number n which determines the repeated differentiation, n time differentiation. So this is these are the syntax. Okay, but if you want to calculate the different derivative of a function using ordinary using the direct method, we have the formula, and at this moment at this point of time I would like to remind you about that. It would be useful to recall that formula because it is very fundamental. So that will bring to you in your mind many ideas about the differentiation. Because it's an important formula, that formula is f dash of a is equal to f dash of a equal to limit as h tends to 0 of f of h a plus h minus f a divided by h. By this we mean, what do we mean by this? And by this formula we mean that we are finding the limit of the expression f of x f of h plus a or f of a plus h minus f a, that one divided by h, as h tends to 0, allowing h to tend to 0, and we take the limit, and that limit it will be a quantity. If we specify the point at which we evaluate, then you will get it as a number. Otherwise, if we try to find this quantity, find this limit at the variable point x, then you will get it as a function. You will get the limit as a function. So these are the two situations. When you specify the point at which you evaluate the limit, then you will get a number. If you do not specify that point, and then you are allowing that point to vary, then you will get the answer as a function of x. That will be then an expression of x. So that expression will be called the derivative of that given function fx. Yeah. Okay, this is the basic idea about the differentiation. Sorry, the basic idea behind the determination of the derivative of a given function. Okay, and this method, the same method we will use to solve some problems that you are going to see in our discussion. And when there is an equation given fx, given that represents a curve on the plane, suppose this is fx, this is the curve that represents the given function fx. You just suppose that, then at this point you consider 2 points. Here you can see 2 points are taken on that curve. When we find the derivative at a particular point, for example, you take this point, you know that the meaning of the derivative, about that meaning of the derivative, that's the derivative at that point, at the point at which we find the derivative, that value, the value of the derivative can give the slope of the tangent which touches that point, which touches the curve at that point. So we can repeat it. What is the meaning of the derivative at a point on a curve? When we calculate the derivative, and the quantity obtained as the derivative will be the tangent of the so it will be the slope of the tangent. That was you can say that it is the slope of the tangent, line. You can see, if you consider this point, this is the tangent. This line, this blue line, is the tangent, and when this line meets with the x-axis, it makes an angle there, and that angle, the tan of that angle, is called the slope of that line, and you are going to get the slope of that line, slope of the touching line at the point of consideration, at that particular point of consideration where we determined the derivative. So that is the physical meaning of geometrical interpretation of the derivative of a curve or a function at a given point. Okay, and that has this idea has some use while solving some problems, and so that point should also be in your you should be aware of that fact. Next, you are going to see a problem. This is the problem. Calculate the derivative of fx equal to the function. A function is given here, fx. Calculate. You have to find the derivative of that function, x raised to 4 by 3 at the point x equal to 1, using the point-wise definition of the derivative. It's the method. It's a method, but that method is very lengthy. But here it is asked to find the derivative by calculating by using that procedure. That basic way of finding the derivative can be applied at some specified points, and these points will be determined in the beginning itself, and at those points we will find the value using a relevant formula. But and that can be used to, after obtaining that values, you can see that in table those values are given. These are the points at which we find the values, and these are the actual values. How many points are there? At 5 different points. We consider 5 different points and corresponding 5 values, and then examining the values of the values which are obtained in the second column. You can arrive at a conclusion about the value of the derivative at a particular given point. But this method cannot be used easily in all cases, because the derivative cannot be determined accurately using this method. This method is given here just to give you an idea about the basics principle behind finding the derivative of a function at a given point. Okay, but we can see how we are now going to see how these values are obtained, and how these values are obtained, and how they are actually helping us to arrive at a conclusion. These values are helping us to arrive at a conclusion about the derivative of the given function. Which function is given here? The function x raised to 4 divided by 3, x raised to 4 by 3 at the point x equal to 1. We want to find the derivative at the given point x equal to 1. This is the problem is explained here. If this is the curve, if the curve of the given function is given here, then the point x equal to 1 is mentioned as mentioned in the question. You can see here in this figure the point x equal to 1 is here, and when you take the point, or when you consider the intersection of the vertical line with the curve, you can see that point. You get that point. At that point you are taking the tangent. After that we find the slope of the tangent, and that will be the derivative. So in other words, for obtaining the slope of the tangent, you can apply the derivative method. Okay, so this figure comes in connection with this problem, this given connection with this problem. Okay, coming to the actual steps of the sagemath sagemath commands. No, first you have to see. First we use the table command. We want to use we have to use the table command to prepare the table. Okay, we first use the table command to tabulate the slope of the secant line passing through the points at a equal to 1. So see, here we mentioned that we take that the given point at which the derivative is to be determined as a equal to 1, and then and also we consider a plus h, another point which is very close to that point a. X equal to a is the first okay, that point x equal to a, but here it is taken equal to 1, and at the point a we add h to that point a, and we obtain a very another point. We obtain another point which is very close to the given point a, and this is ensured by allowing h to tend to 0, or by reducing the value of h in such a way that it tends to 0. Then we see, then a plus h then becomes, since a equal to 1, it becomes 1 plus h in this problem by choosing. But a plus h is in general case, and a is in general case. But in this specific example, since a equal to 1, we get that we can rewrite it as 1 plus h. So by choosing arbitrary small values of h, we allow h to tend to 0. We can find the corresponding values. Now for that you can use, first we want to define the variables. So this is the step in sagemath. The first step to solve this problem is to define the variables. 3 variables we are going to define: a, x, and I. So equal to, we write the command var, then in bracket next we put the bracket, and inside the bracket we put quotation mark, single quotation, and that quotation must contain a, x, and I in the same order, separated by commas. So this declares that these are variables, and we define the next line is the function definition: f of x equal to x raised to 4 divided by 3. That is the given function, and then we specify the point where we want the derivative, that is a equal to 1. After that we write the statement for obtaining the table, for preparing the table, calculating the values specified in this explanation, and for that we use the command table command, and then in bracket we write n into n times 1 divided by 10 raised to I. That then the number of places, actually number of places in which the number here should be displayed will be specified next, but which is then separated, that quantity is separated by a comma from the first part, and so that's digits. So that is the meaning of the this keyword digits equal to 4, and okay, then separated by comma, then n of f of function of f of a plus 1 divided by 10 raised to I minus fa. That quantity must be divided by 1 by 10 raised to I, and then there also we specify the number of decimal places. They are digit equal to 4, and this should be repeated for I. How many times it should be repeated, that is specified here for I in 1 to 5. So 1 to 5, how 5 different cases will be there. Corresponding to these values, corresponding to cases in this list, we get 5 different values calculated and displayed in the table. And the values obtained here, you can see that these values tends to a particular number, and that number equal to 4 by 3, 4 divided by 3. It is then tending to the value 4 divided by 3. Okay, yeah. It's when it is differentiated, then from your experience, that from your mathematical classes, you have learned that its derivative is 4 times x cubed divided by 3 when but at the point x equal to 1, it will give you the value 4 by 3. So 4 by 3 is the value of the derivative at the specified point. Which point is specified? X equal to 1 or a equal to 1 is the point specified. Now we are going to see that demonstration. We are going to demonstrate this problem using sagemath, and you can see how these commands work. Now already I have done that. I would like to copy those things because that will help to avoid the wastage of time. But where is that given? We have to. Okay. Yeah, it is given here. Yeah. See, I have already prepared that program. Now, one line by line, I will copy and paste it here. When I do this, when I copy and paste a particular line, normally it should be typed. Letter by letter it should be typed. But in order to save time, I am doing the copy and paste method. Okay, and then the second line, its fx equal to the function definition. You can refer that manual also. Okay, that must be in the second line, and then see a equal to 1. A equal to 1 will be copied and okay, and then the last one the same thing which is given in the manual. It's the same thing, you can verify. Okay, table, so that enter command, but you can see that in the manual it is split, that single line, single expression is split at this point after this bracket, and the remaining the rest of the that line is displayed in the second in the next line. So actually you can you can write it as the continuation of the first line when you type it in sagemath. Okay, then by taking the output, I am going to take the output. I give that I have pressed that key, corresponding keys to obtain the output. You have to wait. You can see that now you can see that the values are displayed in the table. Thus we have obtained that output. Okay, now by going through that by comparing that values in the second table you can see that it is tending to, these values are, the values are going to a particular number, and that number you can see that that number is 4 by 3. So that way you can conclude that the 4 by 3 is the derivative of the given function at the specified point. But you know, this method cannot be applied as an easy method in all the cases. You know, it's a lengthy and difficult one, and also another important problem is that it will give you only an approximation of the derivative. So you have to get some approximate conclusion about the derivative. You have to derive it only approximately. So that's the main drawback of this method. So for that we have very nice commands and a very simple method in sagemath to obtain the derivative of a given function. That those things we are going to see very soon in our discussion. Okay, now we are going to see another method that can be used too. That's also some way we can say that it's direct. We can say that it's also a direct method. You know, there in this method, you know, we the basic expression, that basic expression is f of x plus h minus f a divided by h. You know, this expression is first evaluated, and after that, first it is evaluated, then we apply the limit. We then take the limit of that expression, and the result of this expression, and allowing h to tend to 0, we get the derivative. So that method, the direct method, can be used to find the derivative. So for that, you know, what we can do, you have to take this expression, you have to console this expression and then expand it. You have to expand it thoroughly, completely. That expression must be expanded. Now for expanding that, you can use the command simplify full. That command can be used, and you can we are going to try that. We can try that also. See, because already we have defined fx, so that function is there in the memory of the sagemath system. So we can try this command, and let's see what we are going to get. Yeah, I have done it. I have completed that copying, and then yeah, I'm going to take the output. Okay. Yeah, it is. You can see one way that is not that expression displayed here. What's the problem? Let's see. X f of x a plus h. Now that says that this is the function, might be some different function, which is actually this expression is not displayed there. So that means the system has some different function stored in it. I think so. F of x equal to okay, x raised to 9. No, this is not okay, x raised to 4 actually. So how we get this? X raised to 9, and then x raised to 8, x raised to 7, this much times, but h is not there actually. Okay. That means something else is there stored at the place of the location of f of x. Some different function is stored, I think. That's why we are getting this expression. So you can see x raised to 9, and then x raised to 8, x raised to 7, x raised to 6. All the terms are there. Okay. it is then x plus h. Okay, we want to change it. Okay, let's try with a different function. Let's f of x equal to, I am going to change the name of the function just to check whether there is any error that has happened with the content of the given function given used there as fx. I want to check it. For that I am going to replace the function name by some other name. I mean a new function is going to be defined. So L of see, I write L of h, LH, sorry, L of x, LX, or some kx again. I define it as kx equal to x raised to 4 divided by 3, and then see, I'm going to use this. Okay, I am going to copy this and see, but before that yeah, we will define x as a h as a variable. Okay, okay, we define h as a variable. Let's define that h equals var. We want to, I think somewhere it is already defined. Anyway, we can define it again, variable, and then inside the quotation you have to write it again. So that's this way we have defined h as a variable. Now h is a variable, and then let's see, I am going to copy this command and paste it here. After that, since f is used there, and the new function we have defined the new function as k. We have given that we have changed the name of the function to k. So everywhere, wherever, at every place where f is present, you have to write k. See, k of a plus h, that's k of a plus h minus k of a. Actually it was f of a plus h minus f of a divided by h, but now it has changed to k of a plus h. We have to change it to k of a plus h minus k a divided by h, and then simplify. We want to simplify it completely, so dot simplify it full command can be used, and after that I am going to apply that output. Yes, now you can see that that error has been rectified. So now it is clear. I can explain the reason for that error. What was the error? Actually, we were expecting to obtain this function, this output, this expression as output. We were expecting while doing that command, while running that command, we were expecting this highlighted expression as output, but no, in reality, but we didn't get that. Actually, we got a different expression, a very lengthy expression. So that might be due to the fact that some different function was stored at the location of f of x, and then when we write this expression and this function as f of f a plus h and minus f a, etc., then that function actually started working and gave us this lengthy expression. But I changed by leaving that function. By leaving that function without considering it, I newly I defined a function. I have defined here kx in that line, the input line, I define kx equal to x raised to 4 by 3, and then I define a variable. Newly I define a variable because we want to tell the system that h is a variable. So actually that was done here in the case of a, x and I, etc., and that was done here. But since we use h as a variable, and we want to tell the system that h will be used as a variable, so this command is included. And after that, I use the same command, but with the small change that all prices where f appeared in that expression, I used k. I replaced every f by k in that expression, the previous expression there, and then what did I do then? I took the output. When I took the output, I got the expected output. We can compare it with the one given in the manual, 1 by 3 into h cubed plus 4 by 3 into h square plus 2h plus 4 by 3. 1 by 3 into h cubed plus 4 by 3 into h square plus 2h plus 4 by 3. The same expression we got. Thus, we have successfully completed that step. Now, using this expression, you can say that we can obtain the derivative by allowing this expression to change, allowing this expression to reach the value when the quantity, when the variable h is allowed to, or by allowing the variable h to move to 0. Gradually reducing its value, h is allowed to reduce its value, and finally it should end at the point it should take the value h equal to 0. So what happens to this expression then? The first term will be 0, will become 0 when h equal to 0. The second term will be 0, third term will be 0, and finally you will get 4 by 3 as the answer. So that will be the derivative of the given function. So this way you can calculate. This is another way of calculating this. So what is that way then? You can evaluate. Simply you can evaluate this expression, and after that you can apply h equal to 0 in this expression. That expression you are going to get, in that expression you can apply the value h equal to 0. Then you will get 4 by 3 as the answer. In this case, you get, or in general you can say that you will get then the derivative of the given function at the specified point. So that's another method. But that method is also lengthy, but this is the or this way you can recall the procedure actually, which method can be used to find the derivative. That method can be brought in your mind. You can think about that procedure, and that will be very helpful to you when you try to solve a similar type of problems. So that's the purpose of this discussion actually. It's because you can say that, or you are going to see that very simple ways are there using sagemath to obtain the derivative of a given function, just by using a very small command, not even very lengthy, a very small short command can be used to find the derivative of a given function. So that way it's very easy, but we are trying to recall the basic ideas. Okay, so after completing this method, we are going to see one more way to obtain the derivative. that is using the limit function in this method, but basically the procedure, the steps are same, but at the end of that procedure you are going to apply the limit, or you are going to take the limit of this expression. It's very simply in very simple terms we can say that first we find the value, find this fraction, find the value of this expression, that's f of a plus h minus f a divided by h will be evaluated, and after that we will apply the limit. We will take the limit of that expression allowing h to tend to 0, or taking allowing h to move to 0. You can find the limit of that expression. How can we write that? Yeah, you can use the limit command. In the limit command, after writing the limit command, you can put a bracket. Inside the bracket you can write f of a plus h minus f a. In bracket you can enclose it in bracket, and that can be divided by h, and then you can put a comma, because this is the expression part. The expression, which expression? This is the expression that we are going to find its limit. We are going to evaluate the limit of that expression subject to the condition that h equal to 0. So applying the condition that h equal to 0, we are going to evaluate the limit of this expression. For that you have to say that the value, the particular value of h, okay, or the nature of h you have to specify. For that you can put a comma and then specify the nature, h equal to 0. Then you can close the bracket. See, this is that this way you can calculate that limit. Then at that moment when we take that output using this command, you will get straight away you will get the value of the value of the derivative you will get directly. But you can see, you are going to see that I am going to demonstrate that. But one thing, when you cannot just copy it as this expression, in that you can see as you can see the expression, as you can see, you cannot copy it and apply it, because we have I am going to copy it now, but we want to make a change. Why that change we require? Because we have already renamed the function as k. So if f is appearing there, that function f was renamed as k. So wherever f is there, you have to use k. Okay, there are two places where f is used in that expression. So I have changed that that function name, the name of the function I have changed at those two places. And now you can take the limit, can find the value of the limit. Okay, see that you can see that answer. You can see the output, it's 4/3, and that is the value of the derivative. So these are the three methods, but these three methods actually directly uses the basic principle. That is the first that method is called the direct method. We can say that it's the direct method of finding the derivative of a function. So this direct method is used in all the three cases that we have explained, that we have seen here. Okay, now you are going to see, we are going to apply some commands to obtain the derivative of a given function. That is the next we are moving to that discussion now. But before that, before going to that part, we can see an application of the derivative. We can see an application of derivative in the given See, then the derivative can be used to obtain the tangent or the equation of the tangent. See, equation of the tangent can be determined as explained here. If the equation of the line is fx, suppose the equation of the curve. Suppose that the equation of a given curve is fx, and also we suppose that a point is specified x equal to a. A point is given x equal to a, and suppose if we evaluate, okay, now we evaluate. You just think that we evaluate the derivative. We evaluate the derivative of fx at that point, at the specified point x equal to a, and that is f dash x. We find f dash x at x equal to a. That means f dash a we find. Suppose we find f dash a. So we have fx and the specified point x equal to a, and we also know that we have determined f dash a. Then if you write the equation y equal to f dash a into x minus a plus fa, see this expression, this equation, consider this equation, y equals f dash a into x minus a plus fa, and this is an idea which is taken from the starting point for the basics of the calculus, or the basic classes of basic topics of calculus. This idea is taken from that, from the basic ideas of calculus. This point is taken. So then what is the importance of this? You can say that this it's the equation of a straight line. Why? Because here in this expression, x and two variables are there. X and y variables are used in this expression, x and y. You can see that, but these are some values. Some values means some numbers. F dash a, it's a calculated value. It's the derivative at the point, derivative of fx at the point a, and a is a constant. Also fa is also a constant. But x and y, and these are variables. X and y are variables. Because of this, I also due to the additional fact that the degree of the variables x and y, are here 1. Since 1 is the degree of the variables, it's a first degree equation, and this first degree equation then can represent a straight line. So in short, you can see that this is the equation of a straight line. So what is the relevance or importance of this straight line in connection with the given equation f of x? So this is very fundamental in calculus classes. It's a fundamental idea that everybody study in the classes of calculus, and that idea can be explained using a figure. This figure contains the curve. This is the curve of the given function fx. This curve has the point. You can see that it in addition to that, it contains a straight line, this blue colored line, straight line, and this straight line touches the curve at a point. That point of contact, you can say which point is the contact. You can see it in the figure, and at the point of contact, whatever is the point of contact, that doesn't matter. But at the point of contact, the given line is a tangent to the given curve, and at that point, this tangent line has a slope, and the slope of that tangent line will be given by f dash a. So this is the equation. You can see the equation given here, and that equation is y equal to f dash a into x minus a plus fa is the equation that represents this straight line. Yeah. So if fx is the equation of the given curve, and a is the point, suppose a is the point here, x equal to a is the point here, This is the general situation. We are explaining it in a general way. So suppose x equal to a is a point here, and when you extend this point, you can see that it touches that point of intersection of the curve and the straight line. And so at x equal to a, you can say that at x equal to a, the curve has the tangent line. The curve has the tangent line at x equal to a. Then the equation of the tangent line can be given by the equation by the equation y equal to y dash a into x minus a plus fa. Okay, so you can recreate the situation in the given example. You can use that. You can use these commands to visualize this. Visualize the situation, and let's write this. We are going to demonstrate the drawing of the plotting of the given curve and the tangential line to the curve at a given point. We are going to explain that. Okay, for that you have to copy this. So by using copy and paste, let's see whether it's going to give you the result. We are going to examine that. Now you can analyze that. Expression. So here in the first expression, the first statement. See. We begin with the g1, and it's a variable actually. Automatically that variable it will recognize it as the system will recognize that g1 as a variable, and that variable is given in the plot. A plot is assigned to that variable g1. So we write g1 equal to plot of fx. So this command says that we are going to assign the plot of fx to that variable g1. In addition to that, fx contains the variable x, and that x can range. The range of variation of x is specified here from -3 to +3. So in the figure, you know, the range of variation of the curve will be from -3 to +3, or the curve will be displayed from -3 to +3 only in that figure, because only those values of x which belong to this interval will be considered for plotting that curve. And then y minimum is -3 and y maximum is +5 given here. So in the upward direction, y equal to, you can measure y equal to 5. Up to 5 it will be, the curve will be displayed in the upward direction. The downward direction it will be the whole curve, the whole figure will be extended in the downward direction up to -3. So these two values, these two y maximum and y minimum values mentions in the upper limit and lower limit of the figure actually. And then figure size is given equal to 3, and the color is also mentioned here, color equal to black. So the curve must appear in black color. Thus, since I have you can see, since I have copied it in the in the sagemath input box, but an error might have occurred. That is due to that the quotation. When you should be careful when you copy a quotation from some other source, quotation mark from other source, because that may not come in the proper understandable way. Actual quotation mark will not appear there, will not be copied there when you use the copy and paste method. So for that, directly you have to type it, and then BLACK color is to be mentioned. So cancel that remaining portion, but that bracket is removed. Since that bracket is removed, you have to put that bracket. I included that bracket because that was removed. Okay, now that first graph we have done for that first, for plotting of the first graph, and then next we go to the differentiation. You know, that differentiation function is used here to differentiate fx. So we want to differentiate fx, f of x, and we name it, the derivative of fx will be denoted by f of x. It's only a function, it's only a definition that we use, we give that definition, but f of x is a new function. F of x or a new variable here. It's a function, a variable part that stands for a function. That variable actually carries the derivative of fx. So let's do that. Let's copy that. Okay, and then is there any chance of occurring an error? I think no. Okay, and then we copy. After that we copy the last statement. Will be copied, but what happened? Error. Okay, that must be deleted. And part by part we will copy it, because up to this portion you can copy. Okay, after that figure size, and then max. Okay, then remaining part color is not mentioned. Figure size 3. Okay, let's complete that. Let's finish it. Okay. Now we have plotted two graphs. Two graphs we have plotted, but still it is not. No, it is not displayed there. To get that output, we want to get the graph as output. For that we have to do some more additional steps. We have to type additional steps. Okay, how can you take that output? Let's think about that. Now for that you have to, since we require both curves together in a single figure, for that you have to type the new function g. G is being used in our discussion for taking plot, or for storing plots and taking the output. Okay, so g is equal to g1 plus g1. We want to add the first plot and the second plot. So g1 g1 plus g2. Okay, so we have combined that the two curves, and then let's take that output. To take the output, you can type g and wait. Will you get an error, or will we get an? Yeah, we have got that. We have obtained the curve. Yeah, success. Now this is the curve. This is the curve of the this is the curve of the given function, and the tangential line, both you can see the tangential. For obtaining the tangential line, you can see that function, how that function used. You can see for that manual plot here. In the second function we have typed, we have used double f of double f a. Actually we use double f a. This is the derivative. This part is written here. F dash a part, f dash a is written here, double f of a into x minus a. You can see x minus a, then plus f a. Okay, so this is the function. This function is written there in a suitable manner there in this in the second plot. and after that x, the variable x is mentioned, then range of variation of x is there given, and then y value, upper limit, lower limit of y and upper limit of y are given, and figure size equal to 3 is mentioned as 3. That when it was implemented, when it was executed, when the command was executed, then you got that output. So this can be taken as an example of plotting of curves also. Okay, now what next? We are now moving to another area where this area our discussion is much simpler than the previous discussions. Here you can see that expression for the formula for obtaining for finding the derivative of a given function. If fx is the given function, if fx is the just imagine that fx is the given function, then its derivative of dash x equal to limit of f of x plus h minus fx divided by h, where h is allowed to move to 0, allowed to tend to 0. That is, we want to take the limit of this expression as h tending to 0, and this is the concept behind the derivative. So this concept can be used to find the derivative. That was the content of the previous discussion, but now we are going to see in the direct method, so method of some direct method of obtaining the derivative. So here the question, you can read this question: compute the derivative of cos x square and evaluate it at the point x equal to root of pi by 4, square root of pi by 4. This is the question. So you can see the solution given here. First the function f of x is defined according to the one given in the question. You have to define that function f of x equal to cos of x square. You can see that cos, first you write cos and then x square is written in bracket. And then you can see this is the statement, the second statement that we are going to use, DIF of fx. And of course this means the command, it's new to you, and but you know in the beginning we discussed about that DIF of, but we are going to apply it for the first time, and so DIF of stands for, once again I would like to remind you about that command, the meaning of that command DIF of. It will give you the derivative of the function that is used inside the bracket as an input. Okay, so DIF of fx, if you write, then it is the entire thing, the whole thing will going to give you the derivative of the function fx. But previous the function is already defined, f of x equal to cos x square. So when we apply this much portion, you know, this much part, it is now clear that we are going to get the derivative of cos of x, cos x square. Then you can see after that you can see that some dot is used, and then substitute command is also used. The substitute command in sagemath stands for substituting some value for the variable inside a function. Any function that you can use along with the substitute, you can use along with a given function. The command substitute can be used, but you know you have to specify which quantity must be substituted for which variable. So in substitute you write x equal to square root of because it is asked in the question to find the derivative when x equal to root of pi by 4. So we want to substitute x equal to square root of pi by 4. So properly it should be included using the actual required number of brackets, opening and closing brackets. See that is a common error that can be made by especially by beginners beginners of programming by beginners of programming. The number of brackets may be different. I mean, some opened bracket may not be closed properly. The beginner a beginner programmer may do such kind of mistakes, so that should be avoided. Okay, and then we by this we have completed that the entire steps for obtaining the answer to the question. So we can now move to the demonstration part. We can try to apply this commands to obtain the derivative. You can see that this is actually the output, the derivative of the given function at the specified point is given here as output. So we have to check whether you are going to get the same output when we execute the command. So let's copy that first function fx equal to see. To avoid the replacing of already existing, some function value is existing, some function is existing in the sagemath system at the location of f of x. So I don't want to erase it or replace it by this new function. So we will we can use a different name for the function fx, and then which name we can use. Okay, okay, px we can use px. Okay, it is now renamed as px. P of x equal to cos x square. Next, the command that can be used to differentiate the function. See, our function in the demonstration we have renamed that function as px. So that function must be used. The corresponding change must be there in the steps that we are going to use in the as the continuation of the first step. So when we copy it and paste in the input cell, you have to make that change. Already we have changed that function name from f to p. You have to make that corresponding change in the second line also. Okay, now different diff of px dot substitute x equal to square root of pi by 4. Okay, now it is complete. We can try to take the output. Yeah, you can see that output is there is no error in our typing, and you have got that value minus 1 by 2 to square root of 2 into square root of pi, and that let's compare it with minus 1 by 2. So we are getting that exact number that you can see here. Yeah, we have got that. Okay, so this way you can use one can use this command to obtain the derivative, and see, it explains, and this problem explains how to use diff command along with the given function to obtain its derivative, and simultaneously how to find the value of the derivative at a given point. Okay, what next then? Okay, now we are going to see another another example of an example of a function which can be called a split type of function, a function which doesn't take single function value. See this function f of x which is given in the example 3 dot 1 dot 3, you can see the function fx is defined as cos x by x if x is not equal to 0 and equal to 0 if x equal to 0, means otherwise it's equal to 0. So fx equal to I repeat again, I repeat it, fx equal to cos x by x if x is not equal to 0 and equal to 0 if x is equal to 0. Okay, how can we, this kind of functions can be called the splitter type of function, and there is no single, the main character of this function is that the expression, function expression take different forms. A function takes different forms in different intervals, or for different values of x, the function takes different form, and that is the property of this function. How can we represent this function in sagemath? That's the main question. That's the question that we are going to see. We are going to find an answer to this this question when we do the this example using sagemath. That question can you can get that answer. You can understand how this kind of function can be represented in sagemath. See, since the function contains two parts, the first part is cos x by x. That part can be called f1, and that function part can be given a name f1. So we write the first statement, f1 of x is equal to cos x by x. f1 of x equal to cos x by x, and the second function is 0. That will be denoted by f2 of x equal to 0. And after that, after defining these two functions, which are the two important parts of the combined function, we can use a piecewise command. This piecewise command can be used to define this function, or you can effectively combine the two sections, two parts of the function, and write it as one function. So that single function is given the name f here. F stands for the single function, and this is this function f, and f is equal to, how do we use this command? You can see piecewise. Now this I think there is an error in writing piecewise this way, because capitalization is, I think it is not allowed, because when I used the capital letter I got an error, so I corrected it by replacing capital by small p, and I got that I got the answer when I did that change. So that you are going to see in the demonstration part. So f is equal to piecewise, so small letter p can be used piecewise, and then you can first you can write that interval. You can specify the interval 0 0 equal to f2. 0 0 in 0 corresponding to 0, that interval you specify. Actually that is not the interval, and at the point it's a single point 0, but for that also, that single point can be, that point can be written as, even that can be written as an interval. Starting point and end point are the same, only that is the difference. So 0 comma 0, that point, then it is when it is the point 0, when x equal to 0, function is equal to 0. So f2 is that function. So in this, corresponding to this this interval, we have f2, and in the other cases we have two cases in the remaining part. First part is the range of x in the case of in the first case is from minus infinity to up to 0, from minus infinity up to 0, and so for in that interval, in that open interval, you have to consider the function f1, and in the remaining part of the part of the real line, that is from 0 to plus infinity. From 0 to plus infinity, the function, effective function, is the same function f1 itself. So for that also you can write 0 comma plus infinity, and properly closing opening and closing that bracket, you can put a comma, and you can write the function, you can mention the function there, and then close that brackets to complete that statement. After that, that derivative function, another this method, this command, derivative command, is used to obtain the derivative, but we are not much interested in applying this, the result of the application of the derivative command together with this function, because we are much interested in displaying the piecewise in displaying this kind of piecewise defined function, this kind of combined functions. We want to take the display of this or the plot of, we want to display the plot of this function, and that's the thing we are more interested at this point of time. Okay, and for that we are going to the demonstration. See, I have already done that. Here you can see the definition. Okay, and that's here. See, first line is f1 of x equal to cos x by x. So I will repeat, I will copy and paste here. Okay, then the second line, f2x definition, the second function definition, f2x, and let's see, the function, single function is defined, that spread function is defined, that will be entered in the third line. And what next? Next is okay, that okay, after completing this, we are going to take the plot of we are going to plot this function. Okay, since f is defined as that combined function, so you can use this command to plot. We want to plot f. See, this command, plot f, plot the function f. F is the function which is explained here, which is given here, and with respect to x, you are considering the variable x and its range of variation from minus 10 to plus 10. See, this minus 10 to plus 10, this range of variation considering that, and y maximum equal to 2 and y minimum equal to minus 2. So from minus 2 to plus 2, y variation is allowed from minus 2 to plus 2. So this is the curve, this is the curve, or this is the figure that you are going to get when you apply this next. Okay, by taking the plot. Okay, now I am going to take the output. Okay, thus we can see the same plot we have obtained on that same plot. You can see that, and there is now connection. When you take a when you draw the plot for a wider area, you can see that these functions or the curves are not going to meet at the point x equal to 0. So it is, but it is continuous beyond that. In the from minus infinity to plus infinity, or on the left side of the point x equal to 0, it's continuous. Similarly, on the right side of the point x equal to 0, the curve is continuous, but it doesn't touch this curve, the left end, this lower curve doesn't touch the upper curve, the upper part of the curve, crossing the boundary, crossing the limit x equal to 0. So x equal to 0 acts as a separation. The point x equal to 0, or the line x equal to 0, acts as a separation of the two curves. So that's what we actually that's clear from the definition of the function itself. It is clear, and this nature of the curve is clear. Okay, this is only a demonstration of defining the functions, this kind of functions, split functions, and the method of taking plot of or drawing the plot of such kind of functions. Okay, next thing we are going to discuss, another example. We are going to see we are going to discuss another example, that is, find the equation of the tangent line to the graph fx equal to root of 2x plus 2 at x equal to 2. So what's the question? Find the equation of the tangent line. Okay, find the equation of the tangent line to the graph fx equal to root of 2x plus 2 at the point x equal to 2. The equation of the tangent line is okay, that an equation of the tangent line, that you can find the equation using the formula, that was mentioned in our previous discussion. You can see that formula here, that formula or method, that equation is given here, y equal to fa plus f dash a, or f dash a into x minus a plus fa is that equation. Okay, for that you can use these commands, use these statements. You can using these statements you can find the equation of the straight line. Yes, you can see that but here, instead of y, some different name is used to represent that equation of the straight line. Equation of the straight line will be called, in this problem, particularly in this problem, it will be called L of x, capital L of x. Capital X equal to capital X, even though that position of the terms are changed here. You can write it, if you like, you can write it f dash, write the term, the second term f dash a into x minus a as the first term, and this one fa as the second term. You can change the position of the terms, but that is not a serious thing. Even by keeping it as it is, you can write the expression for that straight line. So see, for that first we define the function fx equal to square root of square root of 2x plus 2. So 2 into x plus 2 in sqrt. Sqrt is the function that can determine square root of any expression. So sqrt is the command. That command can be used to find the square root of 2x plus 2, and after that, the second line we define Lx equal to f2. See, f of the function value at the point. See, the point specified point is a equal to 2. So at the point 2. At the point 2, we want to find the equation of the tangential line. equation of the tangential line. So for that you have to write f of 2 plus, and derivative of fx you have to use diff of fx in dot substitute diff of fx dot, in the derivative you have to substitute the point x equal to, because we want specifically the derivative at the point x equal to. So for that, dot substitute x equal to must be there, then into the quantity you are going to obtain, whatever is the quantity you are going to obtain at this point, must be multiplied by x minus 2. And then for taking it as the equation as output, equation of the line as output, you have to write Lx again. Okay, we are going to repeat. We are going to implement that in sagemath. Answer can be implemented. See fx. Next, that equation of the line can be entered. Okay, then I want to take the output equation of the the straight line. We want to take the equation of the straight line. Okay, then taking the output, immediately, very quickly you got that answer. 1 by 6 times square root of 6 into x minus 2 plus square root of 6. You can compare it with the one given in the manual. Okay, and after that, if you want to plot the equation of for plotting, we want to plot the curves of the given function fx and the L and the tangential line together, and for that you can use a different type of plotting method. See, g equal to, we are going to plot and we are going to draw the graph, and we want to store it at g and the variable g. For that g we can write g equal to plot fx comma lx, then x ranges from 0 to 4. Figure size is mentioned, figure size is given here as 3. So okay, by copying and then pasting it, okay, we can take the output now. Okay, okay, that has been written, but no, to take the output once again you have to type g and enter. This is the curve and the tangential line. See, blue colored is the curve, and green colored one is the line, tangential line to that curve. Okay, you can compare it with this. Okay, then see, one more problem we have to discuss. Find the equation of the line passing through the point P 2, minus 3 and tangent to the graph of fx equal to x square plus 1. Find the equation of the line passing through the point P 2, minus 3 and tangent to the graph of the graph of fx of the curve fx equals x square plus 1. See, here the point mentioned is 2 minus 3. So we have to fix the point x equal to 2. We take x equal to 2, and then okay, it's a lengthy one, and the answer to the problem you can see on the lines. In these lines the answer is explained here. Okay, for that, we have to discuss them one by one. The first part, the solution, and we refer to Q EA comma FA as the point of tangency of our desired tangent line. To determine Q, we compute the slope of our desired tangent line from two different perspectives. So first let's find the slope of the line segment PQ. Slope of the line segment PQ will be determined first. For that we define a variable A. We define a new variable A, and then we define the given curve is x square plus 1. We define it as fx. Fx we name it as fx equal to x square plus 1. And see, the first line, the first statement is to define a new variable A. Then the third statement is m is equal to fa minus 3 divided by a minus 2. Then m will be calculated. M will be then taken as output. See, what is that? What's the relevance of that? Now the derivative, we will then find m equal to fa minus f of a minus 3 divided by it's because m stands for the slope. What is the relevance of m? What does m mean here? M means the slope of the tangent, the tangential line. M stands for the slope of the tangential line at which point? At the point A. Slope of the tangential line at the point A. See, so for that, the point, since it passes through, the line passes through the point A, FA, through the point A, FA. See, you have to take that as fa minus, and then the point, this point is also important here, 2 comma minus 3. The point of contact is 2 minus 3, and therefore by taking this as a fixed point on the line, or by considering this point 2 minus 3, by considering 2 minus 3 as a point on the line, and you can take the other two coordinates of another point, a second point, and that's a variable point. You have to consider a variable point also, and that variable point can be taken as fa and a and fa. And therefore, using that, AFA is also a point on on that line, and then using these two points having the known coordinates. At the moment we can say that we know the coordinate values of the points, so we can write the slope is fa minus 3 divided by a minus 2, and by typing m and taking the output we get that get the slope. Now m carries the slope. Then we the second part, come to the second part. Here we shall determine the derivative of fx at the point x equal to a. Derivative of, so for that we define fx equal to x square plus 1. So see, it's a repetition, fx equal to x square plus 1. So once it is defined, no need to do it again. Okay, then we differentiate, we find the derivative and put and we use substitute command to evaluate it at the point x equal to a. In general, we are trying to solve this problem in a general way. So differentiate fx, dif of fx dot substitute x equal to a, then you get the answer 2 star a, 2a. And then equating the two formulas for slope, this is the way, this way also we obtain the slope at the point x equal to a. So there are two ways we applied to obtain the slope. One is explained here and the other way is explained here. Actually these two quantities must be same, because this quantity stands for the slope. This is but obtained by considering 2 points on the line, on the tangential line. But here the second kind of calculation, we have obtained the slope using the method of calculus, or by applying the meaning of the geometrical meaning of the derivative of a given curve at a given point. Okay, since these two quantities represent the same thing, we can equate them. So we can equate them and then try to solve. You can use the command solve command. Solve m equal to derivative of fx, then dot substitute x equal to a, and then a. See, m stands for this quantity. At the location of m, the quantity now stored is a square plus 4 divided by a minus a square plus 4 over a minus 2. A square plus 4 over a minus 2. That is the quantity stored at m. So when m is returned double equal to derivative of fx, the derivative of fx, then substituted with x equal to a, this quantity that is 2a will be equated. Nothing is going to happen here except that that equating procedure will be completed here. And comma and n for a, for which value we are going to solve, and since we put comma a, it means that the entire procedure will be done for obtaining the value of a. Then you can see the output will be like this: a double equal to then minus 2 in the square root of 2 plus 2, and a equal to, that means you are going to get two different values for a. Since there are two valid solutions for a, and we have in fact found two such tangent lines, we will get two tangent lines corresponding to the two different values of a. We are going to get two values for a. Okay, that means we are going to get two tangential lines, and their equations are y1 equal to f dash a into x minus a plus f a, as a is equal to as a equal to 2 plus 2 minus 2 root 2, and y2, the second equation is y2 equal to f dash a into x minus a plus f dash a into f dash into x minus a plus f a, as a becomes 2 plus 2 root 2 plus 2 root 2. So this is a mistake actually. There must be, the quantity must be plus, that symbol must be plus, must be replaced by plus. Okay, then we have the steps to plot the equation, to obtain the equation of the lines y1 and y2, straight lines. Two tangential lines can be obtained now using this command y1x equal to derivative of fx dot substitute x equal to a into x minus a plus fx dot substitute x equal to a. Fx dot substitute x equal to a, that is fa. We are going to get fa there, and then dot substitute dot, after that substitute a. You have to specify, you have to give the value, actual value of a as input. Dot substitute a equals 2 into square root of 2 plus 2, and that is the first quantity. 2 into square root of, you see, this is the second quantity, 2 plus 2 root 2. Then dot simplify full, and that will give you the answer y1 full. Then if you take y1 as the output as output, you will get this answer. You must get this answer. And then second function can be second line can be given in a similar way. y2x equal to derivative of fx dot substitute a equal to 0, x equal to a, substitute, then which values must be substituted, x equal to a must be substituted into x minus a plus fx dot substitute x minus a, substitute x minus a dot substitute a equal to minus 2 into square root of 2 plus 2 dot simplify in full. Simplify full, and you can take the output y2 also. Thus you get the two straight lines, equations of the two straight lines. And finally you can go for plotting of the three curves. First curve is fx, and then second curve y1x, third curve y2x together in one figure, and you can see that this kind of figure must be obtained as its output. So up to this stage we have to do many things. Those things we have seen, we have discussed all those things. Let's do that in our demonstration part. Let's do these steps one by one. Okay. After that we can close this video. Okay, for that let's go step by step. And there's chance of occurring error there while doing this, so we must be careful about that. See A and there. Okay, quotation A, then A quotation mark. We have defined A equal to, or you can define A equal to variable A. That way also you can define A equal to variable A. Okay. Then we define fx equal to x square plus 1 fx equal to x square plus 1. And we can define m. Okay, m is defined. Then you can take you can check an output of the steps that we have done so far, because yeah, this kind of taking output will help you to check whether there is any error, whether we have made any error. No error. Up to this stage there is no error. We have got that. Okay, once again, then if you type f of x and take the output, what you are going to get, let's check whether, yeah, you are going to get x square plus 1. So which function, by this we can check what kind of function, which function is stored at the location of fx. Okay, that the function stored at the location of fx is also the correct function. No, so no problem, we can move to the next stage. Okay, and so we can avoid this fx equal to x square plus 1, that's a repetition, because currently that function is stored there. There is no nothing is there to worry about, because that function is there. Now we copy this, and derivative, in this stage we are finding the derivative of fx at the point at the point x equal to a. We are going to take it, and okay, okay, and we want to whatever we have in our mind the answer that we are expecting. Yeah, 2 into a is the answer. Okay, that statement is also correct. Nothing there. No problem there. Next, okay, let's use that solve. We want to solve this. You can see the importance of or the use of the solve command. The solve command can be used to solve an equation by specifying a variable. Here in this command you can see a is specified as a variable. So this expression, you can see this inside the bracket two sections are there, or two expressions are there inside the bracket, which are separated by a comma. The first expression is the expression that is going to be solved with respect that will be solved for obtaining the value of the of the variable which is mentioned after that comma symbol there. Okay, and here the variable mentioned is a. So we will find, we can by implementing this, by executing that command, you can obtain the value of the variable a. Okay, copy it and paste it. Okay, you can then take the output. Yeah, we have got that a equal to minus 2 into square root of 2 plus 2, and a equal to 2 into square root of 2 plus 2. Okay, up to this stage there is no error. We have done right all the steps. Okay, then and these are the two equations of the two tangent lines, because there exists two tangent lines as the figure shows. See, this is the curve, and you can see two tangential lines are there. When we, yeah, since we mentioned the point 2 with the value x, with x value equal to, passing through this point, passing through the given point, this is 2. Okay, the point is which point is 2 minus 3. the point given is 2 minus 3, but the 2 and then minus 3, where is that? And minus 3. Okay, and this is the point 2 minus 3, because the scaling along x-axis is very different from that of that of the scale taken along the x-axis. See the difference of the scales used in x and y-axis. Due to that, you cannot say compare that length or length of one unit which is taken along x-axis cannot be equal to the length of one unit taken along y-axis. So that's why you can see this difference here. But this is the point which is mentioned in the question, the point 2 3, that point is 2 3, where but it is not a point on that curve. You can notice that it is not a point on the curve. It is not given like that. It is not given as a point on the curve, but it's the point which is given as one through which the tangents to the curve. When you consider the tangents to the curve, and such kinds of tangents passes through that given point 2 3, that is the property of the point which is given in the question. So you can see that, referring this figure, two tangents can exist. Two tangents of that given curve can exist such that it passes through the given point 2 3. So we have that's why we have two equations. We have got that two equations. These two equations tells us that there exists two tangents which passes through that given point 2 3 and touches that curve. Okay, and then this is the final step of our demonstration, and then in this step, we are going to display the equation of the curve. Yeah, you want to find the equation of the curve now. Okay, this named as y1. The first one is named as y1. Okay, and it's a very lengthy step, a very lengthy expression, very lengthy expression. The expression is very lengthy, and okay, first let's take that output of the function definition y1x. We are going to take that output. Okay, we have got that. There also in this step also there is no error. For x square root of 2 plus 1, let's compare it with that. 4x 4 into x into square root of 2 plus 1 minus 8 into square root of 2 minus 11. Yeah, exactly, that is obtained as the output. So we can very confidently move to the last part. Okay, okay, let's copy this, and this is for obtaining the second tangent, equation of the second tangent. Okay, okay, done. Then what next? Yeah, you have to type that function name or to get that y2x. Okay, you can take that output. Okay, and that stage also we have completed without error. Without error is we have completed that stage also. Thus we have got the output up to this stage. Next, we are going to plot, we are going to draw the graph of all the three functions together, all the three curves together. We want to bring in one figure. You have to combine, you have to draw the combined figure. Okay, and for that you can use this plot command. So there also you can when for understanding this the structure of that command, you can understand, you can you can go through the you can analyze that statement. You can analyze the statement word by word to get an understanding of that statement. And for that you can see G, this is a variable actually, and G equal to in every plot type expressions we are using G, but it doesn't mean that the use of this letter is mandatory. You can use instead of G any letter A or B or C, but already A is used there in many places, so you must avoid that, otherwise the system will not face some confusion with already defined variable. So for that you have to fix one variable for plotting purpose. Okay, this is G is better. Okay, G equal to plot, and G equal to plot of and then first function fx, and then comma second function y1x, comma then the third function, then close the brackets, close all the open brackets properly, and then put the commas, and then x comma minus x to plus, minus 6 and 6. These are the values of x, the left and right limits of x, and x can x will take the value, take all the values between minus 6 and plus 6 for plotting the curve. And the size of the curve, fixed size is the command to specify the size of the curve. Okay, now we copy it and use it. Okay, and then for taking the output you have to mention again, you have to type again G, and then you can take the output. Yeah, we have got that very successfully. We have got that figure. You can see that curve in blue, and one tangent you can see in red, and another tangent, second tangent in green color. And these the tangents crosses at a point, or they intersect at a point. Well, correctly we can say that the two tangents intersect at a point 2, which has the value 2, x value 2, and the second value y value equal to 3, sorry minus 3, y value equal to minus 3, as mentioned in the problem. No, this is the point 2 minus 3, and it was actually given in the problem. It was asked to find the equation of the tangents first, which passes through that point 2 minus 3, and this is the point 2 minus 3, and the point 2 minus 3, and then it was asked to draw the figure, and also we determined the equation of the two straight lines which act as tangents. Okay, and by this we can stop this video here, and thank you. Now thank you for listening to the topic on differentiation of functions using sagemath commands.